This is a review session, speed running through A2 syllabus because why not? We are going to review the important ideas about electric fields and capacitors. So these ideas are in chapter 17 and 18 in your A2 syllabus. How many questions to expect here? Normally one, sometimes two. So it's 1 to 2 question, but it is large high mark questions lah. So I'm expecting 10 to 14 marks here. Okay, so it's a pretty important chunk. So if you are thinking about like what are the marks that you want to get for your paper 4 so that you can get the grade that you want, you got a strategy a bit, right? So okay, let's segue a bit and talk about strategy. Okay, whoever that hasn't have this planning yet. You probably have a score, or at least I hope you have a score for your AS out of 130. I don't know what this score is lah. Let's say it's 90. You did okay lah. It's not too good. It's a bit worrying because you know you're at the boundary of A. Then you think to yourself, how much do I need to get for my A2? So you have paper 4, which is 100 marks, and paper 5, which is 30 marks. How many marks do I need such that we hope to maintain our A's or something like that. So you gotta have a number here, you gotta have a number here, because the total number is 260. So in order to decide what numbers you should get, you should always try to refer to the grade threshold, right? So I'll show you the grade threshold for the winter 20 sitting. This is a COVID sitting, meaning we're in the midst of a pandemic and the data will be affected by that. But since we are still in the midst of a pandemic, I'm guessing nothing much will change. I don't know. Again, I can't tell the future. So if I look at this, look for combinations where you have already set for your AS. Okay, so not the students who sit for 5 papers together in one sitting. That is really, really tough. So if you're sitting for 5 papers, then these are your grade thresholds. Okay, so you need about, I guess, to be safe, about 175. If let's say you are sitting for just paper 4 and 5, you have already taken your AS, so you already have an AS score, then you can see that if you want an A, the marks is around 182, 177, 183. I think we will ballpark about 185. There's 189 here, a bit anomalous. So somewhere along there is your marks. Something that you want to get is about 185. So let's go with 185. So now it's basic arithmetic. So if we were to go on 185 minus 90, you need to find 95 somewhere here. Okay. So to get 95, maybe if you have enough preparation, 25 out of 30 for paper 5 is possible. Because paper 5 is just repetition. You do the graph, you write the experiment. Okay. In the off chance where you totally can't do the experiments, this may drop to 23, and then this one is 70. So I would think from the perspective that I have 30 marks to burn in this paper 4. So this can be in my 30 mark budget, provided the other chapters that you study, you can do it well. So as probably, if you've been in my class, I've mentioned many times before, if you didn't score well in your AS, then you have to work really hard for your A2 paper 4. If you have done quite a lot of work and this mark is significantly higher, then this one is okay. So you can use this strategy for whatever grade you want to get lah. And I'll be the first to tell you that a B is fine. An A star is okay. A is okay. B is also okay. C is okay also. All right. So I think as long as you get a C and above, you can move on to your next phase in life, into uni. All right. Unless you have specific ambitious targets. So if you want to have ambitious targets, you have to have ambitious gear, meaning you have to be doing the work since day one. So depending on how much work you have done since day one, you will know roughly where you fall on. And it's okay to say that, you know what, I'm a young person. I'm still trying to figure my life out. So my priorities were all over the place. COVID was hard for me. I think a B is reasonable. That's okay. Because nobody asked me what I got in physics but my students. But that's because I teach physics. No one will ask you what you got in physics in A level. Unless it's a drunken night of partying and truth or dare. Okay, so it doesn't matter. So just think about this in terms of strategy. You can align your brain and adjust accordingly. So instead of mindlessly studying everything and not knowing where to focus on, at least you can tell yourself, you know what, I think this chapter I can do, so I'll focus on getting these marks. Or I think this chapter after review is too difficult, or after I try some past year question I cannot, then I will not do this chapter. I'll do something else, like gravitation and circular motion. You have about 20 marks there. That's a good 20 marks, man. All right. So I'm just going to delete this, okay? You think about that lah. Go back and strategize. You can do it for all your subjects. Okay, so here we are going to talk about electric field. And this four-pillar framework is pretty important because we have seen a similar thing in gravitational field. So if I'm a student, right, I'm thinking of like buy one, free one with a bit of modification. So electric field and gravitational field, we have this force field that we want to study. So when it comes to sciences, right, we want to study something, we use a method to study something. And we use the four-pillar method to go through these four perspective so that we can understand how field works. So it starts off with Coulomb's law, all right? Coulomb's law is a lot like Newton's law of gravitation. Your electric force is equal to Q1, Q2 over 4 pi epsilon naught r square. All right. So what we are talking about is there are two charges. Let's say this charge is Q1 and then this charge is Q2. Depending on the polarity, let's say they are both positive charge, the charge will either repel or attract. Okay, so this is the electric force. This electric force is proportional to Q1 and Q2, so to the magnitude of the charges, and inversely proportional to r square, the square of their separation. This is once again a very weird looking equation for some people. So it is good that you try questions to familiarize how to substitute the constants in for the purpose of putting everything in one place. I will crop the constant from your tables of equation now. So there are two ways to substitute the constant. Okay, you can substitute epsilon naught as 8.85 times 10 power negative 12. This here, you keep your 4 pi, or you can put 1 over 4 pi. But I look at the mark scheme, right? They tend to write the equation in this format. And I know in my notes and in my examples, either me or Miss Ellie's one, we tend to put K in front because we lazy to write so many things. But if I'm exam, right, I will write what they want because I want their marks, because I want the grade. Okay, so you operate accordingly. I don't really think it matters, but just to be safe, make sure you show your substitution clearly. Okay, so this is forces. Force field, we are studying the forces. So whenever there's a field, we want to know how strong that field is. So when we travel downwards, for gravitation, we took force per unit mass. So for electric force, we take electric force per unit charge is equal to electric field strength. Okay, so if you divide by one of the Q, because I want to know how strong the field is here. Let's say I want to know, hey, how strong is the field of Q1 at this Q2, the highlighted Q2 point? Okay, so to do that, we will divide by the charge Q2. So let me go back up here. So the field strength here, E is equal to the electric force divided by Q2 at this point. And because of that, one of the Q2 will go away. So this E, the equation will look like Q1 over 4 pi epsilon naught r square. Okay, so just divide by charge. This equation is also in AS because it's the definition of electric field strength. So again, just to put up the definition, E is electric force. Don't forget your test charge per unit positive charge. So the entire framework is drawn to refer to the positive charge, because we have to refer to one charge ma. Positive and negative charge have opposite behaviors. So we choose one as reference law. Why we choose positive? I don't know. The person Coulomb decides to choose positive. The world is also designed for right-handed people. The world is also designed for extroverted people. So if you are left-handed and kind of shy, you always feel a bit awkward in this world one. Then Asian is designed for smaller people. So if you're taller than usual, the table is always too short. See? So there's no one size fit all thing, including exams, okay? So now we're just trying to game the exam. I don't know why I'm philosophical today. Let's move on. All right, this one go here. We are going to find work done or potential energy. So as usual, you want to find energy, you take force times distance lah. But it's not as simple as force times distance. It's never that simple, isn't it? We are going to integrate. So I'm not going to go through the integration process, obviously, but the electric potential energy, U, and in recent syllabus, they have written it as EP, sure, will be Q1, Q2 over 4 pi epsilon naught R. Okay, you can see it as I multiply by R and then one of the R disappear lah, in the shortcut way, although that is not the reason why. All right, so I will talk about the matter of sign now. So when it comes to the sign, right, we know that positive and negative sign are signs to define two things that are opposite. Okay, so when it comes to positive negative sign in electric field, we have a slight problem here. Let me explain why. Positive and negative sign can be used to represent direction. Yes, normally in vectors. So direction in vectors. So if I say the force is 200 Newton positive and 100 Newton negative, so you expect maybe something like this law, 200 and 100. Or like this, 200 and 100. Basically, they're opposite direction. So direction in vectors, we can use positive, negative. Now we are dealing with point charges. Positive, negative can also have something to do with the polarity of Q. Right? You have the positive charge, you have the negative charge. We can call it other things one, charm and strange, up and down. Remember? Okay, but we use positive, negative, or rather the scientists decide to use it, so we're stuck with it now. But this positive, negative also has something to do with work done. Correct? So positive here, so I think this two doesn't need any extra description. But whenever it comes to work done, right, if the work done is positive, it means that there is more energy. Okay, so positive here means there is a work done on the electric field by some external forces. Okay, so example here is bringing positive charge and positive charge closer to each other. Naturally, it will not happen, right? If you want this positive charge to move here, this positive charge be like, hey, excuse me, Q2 be like, I don't like this Q1. It is the same like me, okay? Because like charges will repel. So this one is your Fe. So this is an example of positive. The electric field do the work. Sorry, not the electric field. The external force is doing the work, bullying the electric field. Okay? Whereas negative, so this is also very similar to the gases one. CIE is consistent in work done. Okay? So this is work done by the electric field. So example, we bring this positive charge Q1 and then this, let's say this positive charge Q2. We bring it further away. You don't have to do any work. The electric field will help you. The electric field is like, okay, I'm happy to push you away. Okay, happy to push you away. This is the Fe. I'm just going to draw this to represent this Fe. And this one is external force. You need an external force to bring Q2 closer. the electric force of Q1 will naturally push Q2 away. So work done on or by the field. And this causes a lot of confusion in student because right now we are dealing with all three signs at the same time. You have polarity because charges positive can be negative. We have vectors. Everything on the left side of this table is vectors. So a shortcut for you would be everything that is vector, do not substitute sign. So everything on this side of the table, right? Vector ma. So here is vector. Don't use sign. Don't substitute the polarity. Draw force diagram. Decide whether the force is to the left or to the right. Decide whether the electric field line is to the left or to the right. We will do a question later. Do not substitute the sign. For this one, because of how they define it, which is work done in per unit charge in bringing it from infinity to a point in the electric field, we can actually have a bit of a shortcut. Okay, I don't have time to talk about why and how, but here we will, this is scalar. This is a shortcut to memorize, not used to explain. Explain will look different. So for scalar, we can use the signs. And please use the sign or polarity. Okay, use the signs of polarity. You don't have to draw the diagram. So if let's say Q1, Q2 is positive, you take positive times positive. Q1, Q2 is one positive, one negative, so you take positive times negative. If you are free, you can actually test out the different combination of charges and you will find that it will fulfill this condition one. Like for example, now if I want to bring this one closer to this one, positive, positive. So positive times positive is positive. So the work done is positive, meaning the work is done by the electric field. Okay, so here just substitute the sign. So the definition of electric potential energy is the same as, is almost identical as the definition of electric potential. The only difference here is the term per unit charge. So the definition for this is work done in bringing the point charge from infinity to a point in the electric field. And then this is work done per unit charge and per unit positive charge. This is their favorite lah. They like to ask potential because potential is new. All right. So the last part, when it comes to potential, we travel downwards, we will take potential energy per unit charge. Okay, so divide by Q, meaning this equation now will look like V is equal to Q, let's say it's V1, so it's equal to Q1 over 4 pi epsilon naught R. Okay, just like this one is E1. So for this equation is given, the last one as usual. They will give you this one, and you are supposed to cross-relate across this thing, a lot like gravitational field. All right, but they will test this model more severely here. Okay, one special connection that CIE love to ask is this part here. Remember? Potential gradient. So when we go from left to right, we integrate, go in the opposite direction, we differentiate, right? So dV over dr is equal to E. But there's a negative here. So if you try to differentiate this one, you will get this one. 1 over r ma. You differentiate 1 over r with respect to r, you get negative 1 over r square. See? So from here, a very important relationship is E is equal to negative potential gradient. The frequency of this idea being tested is anomalously high. I'm not sure why, but they think it's important, so okay. All right. So this frame, you need to know everything before you can answer anything in this chapter, unless you are very lucky and they ask you a very easy question. I don't know. I don't know. You know how lucky you are. I don't. Okay, so that's it. Some sidebar explanation would be to explain what happens inside a metal sphere. Okay, so inside a metal sphere or any charge conductor, because these charges they don't like each other, so they will distribute itself evenly around the surface of the sphere. So this is the first point. They will ask you why the electric field inside zero. Well, point number one, the sphere is a conductor, so the charges can go anywhere they want within the sphere. So if let's say you put positive charges in the sphere, they don't like each other, they will stay at the surface one because at the surface they are far away. Think about a basketball. Okay, so let's say you want 2 points on the basketball that is furthest apart, you will take 2 points on the surface, not in the center of the ball. Okay, so it will distribute itself evenly along the surface. So because of this, for any point outside the spherical conductor, so any point outside here, we can assume that it is acting like a point charge. And then sometimes they will ask you what happens inside the sphere. So outside the sphere, it acts like a point charge. I'm going to label this one. This is outside sphere. This one is inside. So inside the sphere, the charges don't move. So if let's say you manage to put a negative charge here, the dude is stuck already. And my dude is stuck because this one will be attracted in all direction. So being pulled in all direction equal to no one pull me. Lor. So the net force is zero. And because the net force is zero, the electric field strength is zero. So this thing is zero. And because E is negative gradient of the potential gradient, so if this is zero, then this gradient is flat. All right, so for some reason, they also like to ask this graph. So that's good. And then they ask you to explain the general, the stuff over and over again. It's the same thing. You will see later. All right, time to pull up some questions. Let's try the ON20 42, I believe. 41 is actually in your test one. 41, you should try or review because this one was set in your test one. Of course, we will recycle papers. What are you talking about? Someone did the job for me. Why would I want to set another paper? I'll set other things. Okay. So ON paper 41, you try and review. We're going to do ON20 paper 4 question 5. Okay. So got this one. Okay, let's just look at the question first. Many lines. Not sure how you feel about that. And then we are going to look at a metal sphere. You know, normally during exam, if I see a paper, right, or if I receive the paper as a student, the first thing I do is I'll flip around. I'll flip around to see where are the easy questions and do them first. But that is also because I know why it's easy for me lah. This is 11 marks. You will develop that understanding if you do enough questions. Cause of strategy. When I see this, I know this is easy already. I want all the marks for this graph. It's done is 3 marks. Because this graph is probably going to look like this graph. Okay, anyway, let's start. State what is meant by the field of force. So field of force, right, whenever we talk about field, we're talking about space. Okay, so we got this is a region of space where this is a general one. So where an object or where a particle experiences a force. Okay, so for example, if it's gravitational field, then it's a region of space where a mass experiences a force. If it's electric field, there's a region of space where a charge experiences a force. If it's magnetic field, it will be region of space where a magnetic pole experiences a force. So depending on how the field, if they ask define electric field, then you have to be a bit more. If not, this is fine. So I'll just put up the mark scheme here for comparison. Okay. Region of space where a particle experiences a force. This is general one. Okay. Specific will be you have to add more context. All right, next. State one similarity and one difference between electric field due to point charge and gravitational due to point charge. The first thing that comes to mind is that gravitational field to point charge and electric field to point charge, the similarities, they both have that, you know, the equation, gravitational force is G m1 m2 over r square, and then electric force is K or 1 over 4 pi epsilon naught Q1 Q2 over r square. You see there's the inverse square law. So I would say both are following the inverse square relationship. Actually, let's be a bit more specific because the mark scheme is not specific, so it's not very good in case they change the mark scheme. So we want to talk about electric field and gravitational field. So both fields field strength, sentence a bit odd, but never mind. Both field strength obeys the inverse square law. Meaning gravitational field strength is inversely proportional to 1 over r square. Electric field strength also inversely proportional to 1 over r square. So I'm not going to talk about the force, I will just talk about the field. This is one option of answer. Second option of answer would be both field lines are radial. Radial means like this. This is mass. So the gravitational field is inwards like this. Along the radius ma. So radial long. So this is G. But if you talk about charge, let's say this is Q. The field line for charge, even if it's positive charge, is also radial. See, they're all along the radial. So this is another option. Okay, what are their differences? The most obvious one would be gravitational field is always attractive. That's why there's a negative in the potential energy. This one, we don't have negative sign. Gravity God. They will even ask you why is there a negative sign, okay? Because it is always work done by the gravitational field. The gravity will always help you pull the object closer. Anyway, gravitational field is always attractive. And then the electric field direction can be towards or away from the charge. So this attractive is towards the mass. I will caution against using repulsive because they prefer that you talk about the field like a direction. For example, if you're drawing negative Q, the field line for negative Q is pointing inwards towards. So this electric field here, we want you to comment on E and G. And then because these two is vector, we'll talk about the magnitude, a statement about the magnitude, like for example, this one, or a statement about the pattern. And then we'll talk about the direction. Mass is always pointing inwards towards the mass. Q can be pointing inward, can be pointing outwards. Okay. There's a table in your notes comparing all the similarity and differences. I will only go through them once I've done magnetic field, so we can compare all three lah. Okay. So here we have an isolated metal sphere, radius 0.15, situated in a vacuum. Great. Common question. Electric field strength on the surface of the sphere. So at the surface of the sphere is 84 volt per meter. So if I find any point here, any point here is 84 volt per meter. Determine the charge Q on the sphere. Wow, very easy question if you know the equation for E. So from here, what we know is E is equal to Q over 4 pi epsilon naught R squared. Can substitute lor. Just substitute. So 84 is equal to Q over 4 pi epsilon naught. Our R, this one is at the surface. So at the surface, the R is 0.15 square. Okay, so press your calculator properly, carefully, should bring you 2.1 times 10 to the power of negative 10 coulomb. So this kind of bonus mark, right, where you state the equation and you put the values in and you get answer, it is worth it to take 1 minute to just pause and make sure you convert everybody to SI and didn't press the wrong constant. Okay, so if it will help your brain, you may want to substitute in the constant 8.85 times 10 to the power of negative 12 by referring to the table. Because it hurts me as much as it hurts you when you lose that mark because of not familiar with the equation. All right. So rewriting the equation will give you 1 mark. So this is C1. Final answer is A1. So final answer with the substitution. So you don't go from here, jump to here, okay? Need to show substitution. At least show this one. All right. Electric field strength at point P, 0.45 meter from the center of the sphere. This one is easy because we know E follow the inverse square relationship. Nah, Q is the same. We didn't change the charge on the sphere. We didn't change 4 pi epsilon naught. Didn't change anything. So from here, I can say E1 over E2 is equal to inverse. So we flip R2 over R1 square. Okay. Or write however you want to write the ratio. Okay, so the first electric field strength is 84. The second, I don't know. All right. The second radius is 0.45 square. And the first radius was 15 cm at the surface. Sorry, 0.15 meter at the surface. So what I have with me now is 84 over E2 is equal to 3 square, right? Because 0.45 over 0.15 is 3. So divide lor. E2 will be 84 over 9. It's 84 over 9. Ding, ding. 9.33333. 9.3 lah. Volt per meter. 2SF. Okay. Alternatively, some students be like, Miss, actually, we have everything we need in this equation. Can I use the equation again? Sure. You can use this again. Instead of 0.15, this one you put 0.45. I repeat the calculation again, because we have Q already, right? So what you will do is you will put 2.1 times 10 to the power negative 10 divided by 4 pi epsilon naught 0.45 square. You will get the same answer. Okay, I prefer to use ratio because ratio is faster. I just say 84 divided by 9. Easy to press calculator. I don't need to include all the prefix. Okay, next. Use the information that you calculated and show on this graph the variation of electric field strengths with distance from the center of the sphere from 0 to 0.45 meter. Okay, so our sphere is here. Let me draw the sphere. What's the radius of the sphere again? 0.15. So this means that here is the radius of the sphere. This is RE. I mean, radius lah, R. Radius of the sphere. This point. So in the interest of helping you visualize, I will draw the sphere on the graph and hope for the best. So the sphere will be something like this. Wait. It's fine. Ding, ding, ding. 1, 2, 3, 4, 5. Okay, let's see. So center of the sphere is somewhere here. Center is here. Okay, good enough. I'm satisfied somewhat. So this is the position of the sphere, right? I think the center is somewhere along this line here. Somewhere here. So here to here is your radius. This is 0.15 meter. So at 0.15 meter, the electric field strength, I'm going to just draw a table for the people, okay? R on the surface 0.15 meter. The electric field strength is 84. At 0.45 meter, the electric field strength is 9.3. So let us plot 84 first, okay? 84 is 2, 4, 6, 8, 10. So 84 is here. I zoom in. Okay, 82, 4, 6, 8, 10. 84 at 15 cm. Second coordinate 0.45, 9.3. So 0.45 is middle here. 9.3, 2, 4, 6, 8, 10. So 9 is somewhere here. Miss can plot in between boxes like this. Paper 4 can, paper 5 cannot. I'll be safer or I'll be happier if I have another point. So I think I'll just find 0.30 meter. This is 84 divided by 3 square. Because here to here, you times 3 ma. 3, 3. Inverse square relationship. So if here to here you times 2, then whatever this one is will be 84 over 2 square. Which is 84 over 4. I just want another point. So this one is 21. So when 0.3 will get 21. 21 is here. So I'm going to join this in a smooth curve. Smooth curve. I tried. Okay. Smooth curve. Stopping at here. Something like this. Don't forget to draw inside the sphere as well. Inside the sphere, there is no net force, so the electric field line should be 0. But I will draw something like this during the exam. And because I really want these 3 marks, I will help the examiner by labeling one. Inside the sphere, E is 0 because there is no net force. Okay, so your graph look like this. If you want, you can draw a dotted line. The dotted line is not necessary. Okay, so where are the 3 marks? The line E equal to 0 here will have 1 mark from 0 to 1.5. Okay, and then there's a curve, smooth curve with decreasing gradient and passing through the point, smooth curve plus the coordinate, smooth curve plus passing through the coordinate 0.1584 plus decreasing negative gradient. Basically the shape is 1 mark. So this part is 1 mark. And then passing through this point 0.45, 9.3 is 1 mark. Okay, so the curve is 1 mark. The curve, including this one, is 1 mark. So if you are not sure about the shape, right, you can always find just another value. It won't take you too long. Just sketch out the graph. And for people who are, you can take your time, build a table like this, and then just draw long. For 11 marks. I think it's pretty okay. So when I see this, I see one thing, I'm very happy. This is an easy question. Easy. Okay, Miss, you keep saying this is easy. What is hard? Okay. So we're gonna move on and do something a bit more different or challenging, I would say. The ones that are recorded, I'm not going to do, okay? So I will do, okay, for something similar like this, something similar, I'll give you some suggested things to try. You can try June 20, paper 42, question 7. I don't think this is recorded, okay? And you can also try for electric potential one. So this is the ER graph or EX graph. Also try ON17 paper 42 question 6. Okay, this is a VR graph or a VX graph. So make sure both graphs are okay. They are fairly similar in nature. Maybe I should do one, but no need lah. I will move on to the next one so we can end hopefully at a reasonable time. Ding ding. Okay, so the slightly harder or the different ones is when I bring in another charge to the party, because one charge sphere is a lonely charge sphere. So you need to bring another charge sphere into the party. FM20, paper 42. Question 6. All right, so these two are single charges. You should do more than this, but especially if you want to try this chapter. Okay, FM20, paper 42. So in this scenario here, we have two spheres, okay, and they draw this weird sigmoid looking graph. Students are always afraid of this graph. Please don't be. They are not hard. They just look very intimidating. But at the end of the day, it's just a curve. You know? Okay, anyway. I will do both types of curve. There is obviously the electric field, and then there's the electric potential one. And you can see this is actually 8 marks. All right. So for this question, we have a sphere A and B. The centers are separated by 24 cm respectively. Okay. And the variation with distance of center A and the electric field due to the two sphere is represented by this diagram. Okay. State the radius of the two sphere. Miss, is like the trial paper. Yeah lah, aiya, where got hard? You just didn't do enough past years. So this one is 2. This is also 2. Because why? Inside the sphere, there is no field. So 2 cm. 2.0, hello, for the nth time. Do not make the mistake of writing 2 and getting 0 mark. Okay, so here, inside the sphere, the field is 0. Write as many times as you need so that you can remember. Inside sphere. How do you think I pass my exam? I write the same thing over and over again until I want to forget. Also cannot. Okay. So here, the charge on the sphere is 3.6 times 10 power negative 9 coulomb. Okay, so this is QA. So label that in. QB, determine QB. Assume that sphere A and sphere B can be treated as point charges at their center. Explain your working. Okay, meaning I need an equation or a statement to show us what main idea you are using. Okay, so the easiest one to think about is right now, Do we know whether it's positive or negative charge? QA and QB. What's the polarity? The telltale sign is actually the intersection point where it cuts the x-axis. So I'm going to zoom in a bit. And I see that it cuts the axis around here. 2.2 point. Yep. 16 can. Can. We'll just take 16 so it's easier. Can we take 16? What do you think? The intersect. Okay. I think more symmetrical is this one. What I do is I count the boxes where the curve almost meet the axis. So this is the intersection point, which is about 15.6. Okay. So this means at this point here, the electric field, the net electric field strength is 0. So let's say this is sphere A, and sphere A charge is this much. I am going to assume it's positive because they didn't say anything. 3.6. So positive means it's pushing away. This is EA. Okay. Then for sphere B to also cancel out EA, this QB, right, should also push in this direction. So QB must be positive 2. Okay, because the net electric field is 0. So if this is positive and is pushing out and away, then QB also must be positive to push out and away in the opposite direction, such that at this point, I mean, I read it as 15.6, but I'll check later. So at this point, 15.6, the net electric field is 0. So that is the main idea that we are operating on. So the resultant electric field of both A and B is 0 at the value of X equal to 15.6 cm. Hence, EA, magnitude of EA will be equal to the magnitude of EB at X equal to 15.6 cm. So we're going to operate on this assumption. You don't want to write the purple one, that is okay, no problem. But you should at least write the blue one. If not, you will lose 1 mark because you didn't explain why you suddenly, for no reason, say that they are equal. So it will be safer if you write a purple one, but the blue one is generally good enough. Okay. So now we're going to substitute the equation of electric field strength. Okay, say 15.6. Let me check. I think we take 16 now. Sorry, I keep flip-flopping because the graph is kind of blur on my side. I'm pretty sure it's going to be quite blur on your side too. Looks like 16. 16 will be a nicer number. But as long as you explain here, they should account for errors lah. Okay. 16.0. So normally there's a range one. But you have to look at it carefully though. Does it look like 16? I think where it cuts the axis. Can lah. It looks like 16 at this point. Okay, let me amend the diagram. 16.0 cm. Okay, if EA equal to EB and E is equal to KQ over R squared, write everything. Because if we make a mistake somewhere in the journey of getting the answer, I can still get some working marks. So this will be QA over 4 pi epsilon naught RA square, and this is QB over 4 pi epsilon naught RB square. So the 4 pi epsilon naught, you can say bye. Okay, thanks, bye. Thanks for your contribution. Okay. And then you are now, I'm going to put QA and QB together because I can cancel off the prefix if there's any, right? And then I'll bring up the RA and the RB together. Miss, what is RA and what is RB? Well, look here, lor. We are measuring the distance from here to here. So RA is equal to 16 cm, meaning RB here to here is RB. RB is equal to 24 minus 16, 8 cm. So A is 16 and B is 26. Gonna continue here. QA over QB is 16 cm over 8 cm square. All right, A is here 16 and B is here 8. I'm gonna go back here and put it in. We have QA, right? QA is 3.6 times 10 to the power of negative 19. You can check negative 9, sorry. You can check the top part because I have the question beside my face now. QB, you're looking for it. And this one would be 2 over 1 square. So cross multiply, you will find QB as 1 over 4 because 2 over 1 times 3.6 times 10 to the power of negative 9, making QB 9.0 times 10 to the power of negative 10 coulomb. 36 divided by 4, 9 no. 9.0 times 10 to the power of negative 10. So where are the marks? At 16 cm, at x is equal to 16 cm, EA equal to EB. Okay, or the resultant of force is 0 at 16 cm. This one is B1. Okay, B2 would be when I see this equation together with the substitution. So not just this equation, I need to see this equation and I need to see this substitution, some form of this. And then final answer is A1. Okay. Great. Moving on. We now take away B. Using the information from B to determine the electric potential on the surface of A. Well, we know V is equal to Q over 4 pi epsilon naught R. So if we want on the surface of A, we will take QA. And then this is radius of the surface. Radius, as we determined just now, was 2 cm. Or 2.0 cm. Substitute low. QA was 3.6 times 10 to the power negative 9. Since B is not there, we don't have to bother about it. This will be 4 pi epsilon naught times 10 to the power negative 12 R 2.0. Wait, cm. Wow, nearly make mistake. Negative 2. Okay, everybody got to be SI. So if you press calculator for this one, you will get 16004. As I mentioned before many times, if you don't know whether you want to convert to SI or not, and you don't want to think so much, then you convert everybody to SI. If you are lazy like me, then you have to learn when to convert and when not to convert. Whenever there's a VVIP, aka a physical constant on the front part of your exam paper, or the unit here is SI, then everybody have to be SI. Okay, unless a unit can cancel off. Okay, we will soldier on. Calculate the capacitance of sphere A. Chapter 18, yes. Q equals CV. So QA is equal to CVA. Oh, so capacitance will be the charge 3.6 times 10 to the power negative 9 divided by the potential difference. Wow. 2.3 times 10 to the power negative 12 farad. So this question is pretty okay. The only slightly complicated part is this one, where you need to, show the working or explain your working. But let's move on to another one where we need to talk about energy, or we need to write explanation. If it's recorded, I am not going to discuss lah, cause watch the recording more. Then you can save yourself some time. I can cover more questions. So this is paper 4.1, question 6. Watch and try. Or try and watch. Or try already understand, no need to watch. Okay, question 6. This is already recorded. Look at the playlist for the relevant chapter. So this question will look like this. Okay? It's the same situation, but instead of having a charge sphere, you have charge A and charge B. And here you can see this graph is so different than the other graph. It doesn't have a point, any point here where the electric field is 0. So this means, right, the polarity is opposite. Okay? Because the direction of electric field is always the same direction. So they never cancel out. So here you see all this line. They ask you to state and explain. So we've already recorded the explanation, but very briefly, they have opposite sign because electric field is never 0. Okay? They have same magnitude because this graph is symmetrical. The minimum point is right at the middle. This graph is not symmetrical. Which part of it? No, it's not symmetrical. So because it's not symmetrical, the magnitude of the charges are not equal. One is 3.6 times 10 to the power -9, and one is 1/4 less. Because it's 1/4 less, right? You can see this distance, the ratio is about 1/4. Okay. So this is symmetrical. So the magnitude is the same. Okay. Then finally, what else they ask you to explain? Magnitude of acceleration. So if you want to find acceleration, you will think about force. If you want to think about force, you will think about field. And this graph will give you information about the field. So the field decreases to a minimum point and then increases. Always positive, so it's always the same direction. Force decreases to a minimum at 5 and then increases. Acceleration decreases to a minimum at 5 and then increases. So this is not the hardest form because you don't have to think about energy. So go try this one. It's recorded. Think about, go and process it in your brain. Okay, I'll give you 1 or 2 more to try. Another one that you can try, I also think this is recorded because we understand that this is a difficult chapter. So we record many examples so that people can study either while doing the topic or doing revision. So go and find it in the playlist. Cannot find, then come disturb me. Okay, and finally, the last one is ON18 paper 42 question 6. I think these are all recorded. So these are all 2 charges. The only difference is the graph looks slightly different, and this one you have to sketch. Sketch your own graph. Okay, so all of these are recorded. Refer to playlists. Right, so this one all involves energy. It involves electric field strength. I want to talk about the one that involves potential. Potential. Okay, if you want a shortcut, a must try or a must watch or a must do, if you haven't done yet, is the ON16 paper 42 question 6. This is also recorded because this question, it has the electric field graph, very familiar, or then they want to find the ratio of charge. Just now we find the charge using ratio. I'm pretty sure we can find ratio of charge then. Tada, look at this. What is this? Potential against distance. Then they ask you to find maximum speed. This one you must try. Okay? Because this one basically tests all the main idea. This is a all-in-one question. So this is what I mean by must watch. So if you're like, too much already, then at least watch this one more. Okay, I'm gonna find a energy one that hopefully have not been recorded. Then we can do, but let me double check first. Got a bit excited when choosing the examples. So essentially, we just chose everything. Okay, so what we have recorded is this one, see? Okay, the U-shaped one, and also this one. So go and try these questions. They are pretty important examples. Yes, I found one that I haven't done yet. Okay. Point charges electric field. Before we move on to capacitor. Capacitor is not as popular. So sometimes they have questions, and sometimes they just, never mind lah, we just include as a small 2-mark section inside chapter 17. So you should allocate your study time accordingly. As they do ask a full question. We'll see. Okay, so we're going to do May, June 15, paper 42, where I will examine the VR graph. That will be the last example for chapter 17. Okay. So all this is the electric field E-r graph for 2 charge, whether it's charge sphere or just point charge lah. So now we're going to move on to the VR graph. Okay, so this is our beautiful charges all over again. Means they got nothing else to draw. No lah. What else do they want? Do you want them to draw? It's always the same thing over and over again. You other syllabus, not yours, can have up to 4-point charges. But that would mean you need to resolve vector. And I think the intention of you studying electric field is not so much to see whether you can vector or not. So that's why your questions are still manageable. The only vector diagram you need to draw is on a straight line. So it's not that scary. No need to resolve. Beautiful U-shaped graph. It looks like a bowl. Okay, so I'm going to do this question now. I'm going to crop everything. It's a pretty long question. And yes, I should activate my windows, but money, you know, they don't fall from trees. Okay. Define electric potential. I can scroll up and copy, but I'll write for you lah. Work done in bringing a unit positive charge from infinity to a point in the electric field. Okay, if you are very scared to follow, you want to follow exactly the mark scheme, it will be work done per unit positive charge. Positive charge, work done per unit positive charge in bringing it from infinity to a point. So we want work done per unit charge lah, basically. There we go. In bringing it from infinity to a point in the electric field. Keywords here, work done per unit positive charge. Wow, how do you spell charge? It's 1 mark. The other mark is you want to bring the charge from infinity to a point. This is 1 mark. This is M1. If you don't get the first mark, you cannot get the A1 mark. Makes sense what, right? If not, your sentence will be hanging. Bring what from infinity? Okay, so here we have, again, two positively charged metals. I'm going to write a big fat positive here, big fat positive here. Point P is along the line, and the electric potential changes this way. Whee! Okay, interesting. State how the magnitude of electric field strength at any point may be determined. Oh, that is the one that I say they like to ask. You are given the Vx graph, and you want to relate to electric field strength. So the electric field strength is negative potential gradient. Which is the gradient of figure 5.2. Okay. Interesting. You can see that this 2 is positive. So you will expect that your E graph, okay, I'm going to steal this and park it at the side here. You will expect your E graph, let's say I shrink this a bit so I can sketch. Okay. Your E graph will have the shape, you see here, this part is 0 gradient. So this means the electric field here is 0. E equals 0. Because why? dV dr is 0, or dV dx is 0. So you kind of have this decreasing negative gradient, so it will be decreasing positive value. So if you are drawing your E graph, right? Your E graph. Okay, I want to draw on top of that, but I scared confuse people, so I'm going to draw here lah. E equal to 0 here. Dot, 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 dot. So here is where your ER graph will cut the graph. I mean, cut the x-axis. This section here is negative gradient. I write here. This part here, negative dV dx. So because it's negative dV dx, E would be negative potential gradient. So negative dV dx will be equal to positive value. That's why the E here is a positive value. You will go something like this. On the surface of A will be 0 lah. Okay, gonna be like this. And then here, this part here is positive gradient. So positive gradient means negative E. So this part is negative E. Ding, 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 ding. So this, it looks, of course, inside here is 0 lah. It looks a lot like this one, my friend. There. It's the same graph. Okay. So right now, what is going on? Okay, never mind. This one will go down like this. So this actually helps you see the relationship between these two. This gradient is negative, so this value is positive. Turning point here, gradient 0, so this value is 0. This gradient is positive because it's turning upwards. So the value is negative. Okay? So when you want to describe this, of course, good math student should be able to see the gradient now. But if you cannot, then you can sketch it out at the side law. Because in part 2, they are asking you, without any calculation, to describe the forces Describe the forces acting on a positively charged particle placed at point P from 0 to 10 cm. 0 to 10 cm. How the force change? So you can see that if you have drawn this graph, you can describe the force here. Here to here, force decrease because the electric field decrease. At this point, force is 0, your 6 cm. And then here to here, force increase in opposite direction because negative already. Okay? So we're going to write that down in 3 marks. So it's either you draw the graph or you, I guess, mentally visualize the gradient. How comfortable are you with looking at gradients? It's a pretty important scientific skill. If you intend to do more science, anything that's related to science, staring at a curve and knowing how the gradient and the value changes is a important skill to have. Okay, so without further ado, we will write this one. Okay, so let me type it. The wires are all over the place. Okay, come. Force is maximum at the surface of area A. They say describe, they didn't ask for explanation. But in case they ask the state and explain, I'm going to explain in brackets, okay? So force is maximum at the surface of sphere A because the gradient of the graph maximum there. So steep. Imagine you have a skateboard. Tony Hawk's. Okay, so here is so steep. So this means that the gradient of the graph is maximum. All right. Second point, this force will decrease, right? The force then decreases as x increases from 0 cm or from x equal to 0 to x is equal to, where's the turning point? 6 cm, right? This is 6 cm. So from x is equal to 0 to x is equal to 6 cm. Okay. Force is 0 at x is equal to 6 cm. So you can say decreases to 0 lah. Okay, so this one, why? Because the gradient decreases. Is x equal to 0? Yep, x equal to 0. Okay, so force is 0 at this one because the gradient is 0. So this part, when they ask you to relate electric field strength to the gradient, is to prime your brain to relate gradient to field and field to force. Okay. Next, after 6 cm, so you can say after that the force increases in the opposite direction. Must mention opposite direction because force is a vector. So when describing a vector, we should always talk about how the magnitude changes. For example, force increase. And if there's a change in direction or if there's anything relevant information about direction, it should also be stated. So force is increases in the opposite direction from 6 cm to x is 10 cm. It's because gradient increases but negative. But this is positive gradient, sorry. This gradient of the graph, all this is negative gradient. Okay, I'm very paranoid one because I know the mark scheme, right? Or I done enough past year question. So I will also add another point because I don't know whether there is a mark for that. I have to be able to relate electric field strength to the graph, which I've already done in this part, so I don't have to do again. But I also have to relate electric field strength to force. Okay, so I will just say either in the top or let's say as an afterthought or as a footnote, I would say that the electric force or electric field strength is force per unit charge. That's why I can use electric field strength to talk about the force. So the relationship is here. We started off with a Vx graph. Okay, so the first relationship, gradient or negative gradient of Vx is equal to E. This one. This is the first relationship. Already mentioned, so I don't say lo. You want to describe force, we need to relate force to E. Electric field strength is defined as force per unit charge. That's why I related to F. That's why I can use this to describe this, because here is the relationship. So I am wee bit paranoid as a person. So I will write out this part already right in part 1. I will also mention this link to justify why I can use this to describe this. So go through the thought process, draw a flow chart like me if needed, and then write out the statement. Okay, can. All right, what are the keywords and where are the marks? Let me change color so we can see more clearly. Force is maximum on the surface of sphere A is 1 mark. All these are B marks. You don't have to explain. I just put the explanation in brackets. Force decreases as x increases until 0 at 6 cm. This is 1 mark. Decreases. Force decreases until 0 at 6 cm is 1 mark. Force is maximum at the surface of A is 1 mark. I think if I'm a student, I don't want the examiner to mark very fast and don't give me my mark. So I'm just going to put force decreases from x is equal to 0 to x is equal to 6. I'm just nitpicking, okay? I'm nitpicking my own answers. So I put decreases so that when the examiner mark very fast, they see maximum decrease, they give me mark now. Because it's maximum, then decrease, then increase in opposite direction. This is B1. Do you need to state the position? Yes. So you need to mention surface of A. You need to mention 6 cm. The position is needed. Okay, at the very least. And then opposite direction is compulsory. Okay, that's it for the explain part. We're going to move on to the calculation part. The positively charged particle have a charge per unit mass of this one. This is called a specific charge if you do chemistry. Initially, the particle is at rest. Okay. On the surface of sphere A, where x is equal to 0, it then moves freely along the line joining the center of the sphere until it reaches the surface of sphere B. On figure 5.2, mark with the letter M the point where the charged sphere has maximum speed. Use figure 5.2 to determine the potential difference between the spheres. Am I reading the right question? Okay, Ken. And use your answer in part 1 to calculate the speed of the particle as it reaches sphere B. Explain your working. Oops. Did I press something? Okay. Never mind. Okay, I'm going to copy this diagram here and draw this one. Okay, so we want to be able to mark point M where the charged particle has a maximum speed. So one thing about this potential surface, potential gradient, and why we like potential so much, right, is because if let's say there's a positive charge, which we have now, this positive charge is going to travel along this curved surface very much like a ball on a curved track. Think about the ball. The ball will have the most mg downwards here because it's almost vertical. When the ball is here, the mg is less. When the ball is here, the component of mg that is pulling the ball down the inclined plane, which is this one, will be less, smaller and smaller. Does that make sense? So, okay, let me do a bit of throwback first. I zoom in. Imagine this is not electric field. This is inclined plane. Yay. So if this is inclined plane, and I have all of this, the mg is acting downwards, 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 downwards. Mg is the same because gravity. But let's say you want to find the force down the inclined plane. This one is mg sine theta, remember? You resolve. So this mg sine theta will become less and less because sine theta, the theta is getting smaller and smaller. The angle of incline is getting smaller and smaller. Until at this point, there is no mg sine theta. So this is what they mean by the force will decrease until 0 and then increase again. Or you just imagine, you play so many games before, something rolling down the mechanics of your game, rolling down the inclined plane, the force will decrease to a maximum. But it also means that the ball is fastest here and then come up. So point M, I'm going to leave this here for people who need it. I'm going to continue the graph here. Point M is here. This is M. Another way of looking at it is changes in energy. Okay, so you have the largest delta V from surface of A, which is here. Can't even tell what the value is. Hang on, let me check. Surface of A, which is here. This one looks like 570. And then here, what is this? This is 246. Here. Let's take this one. This is 140. It's M140. It's slightly less than 140, but never mind. 140. So the changes in potential here, this delta V is the greatest. Think of conservation of energy. In a normal world, we will say change in KE is change in GPE. So I will take mg delta H. This one will be delta H. That's why we draw the graph like that. So now we are trying to modify delta V. How would the charge behave? The charge will go wee, it's fastest here. So meaning this one, instead of mg delta H, this will be change in electric PE, and this will be Q delta V. Here to here, the delta V is largest. That's why this is your point M. Here is fastest. So from surface of A to M, the ball is faster and faster, faster and faster, faster and faster, fastest here, and then it will slow down at B. Will it stop at B? Nope, because at B, you still have your delta V. Okay, so the potential difference is here to here. This is your delta V from A to B. This is delta V, largest is from A to M. So delta VAB would be 570 minus 230, right? This is 3 boxes. 230, 570, which helps us answer the question here. Potential difference between the sphere. So at A, your VA is 570 volt. At B, VB is 230 volt. Hence, delta VAB will be 570 minus 230. I'm just writing complete working. You just want to write 570 minus 230 also can. This is 340 volt. That's why it's 1 mark. So you just need to show the subtraction leading to this answer. Okay, using this 340, calculate the speed of the particle as it reaches the surface of sphere B. Explain your working. So as it travels from A to B, if you look at this graph, you travel from A to B, there's a change in potential energy. Potential energy decrease, potential energy increase. But there's a net change. So the net change can be calculated using delta VAB. Just like if this is gravitational potential energy, it's the same idea. You don't have to care where the bottom is, you just find the change in height. Okay, so what I would say is the change in electric potential energy is equal to the change in kinetic energy. So change in electric potential energy is equal to change in kinetic energy. But they say explain the answer. So you write like that actually generally is good enough. But if you want to write a statement just to show that you are trying to explain, you just write change in PE is equal to change in KE. Conservation of energy. Change in potential energy is QV. Remember, because V is potential energy per unit charge. But this one is delta change. Charge didn't change, so it's delta V. And we want it to go from surface A to surface of B. So this will be AB. And then this will be half mv square minus half mu square. So this velocity is at B, which we want to find. This velocity is at A. UA is 0. They say 1. See? Particle is at rest on the surface of A. So we are taking from A to B, meaning this whole thing become 0. Beautiful. Okay, I notice here that I have a Q over M. So I'm going to want to use the Q over M later. So I'm going to put it here so I can. Too much, giving you and me motion sickness at this point. Okay, so I'm going to bring the Q over M on one side. So Q over M is here. I can substitute later. I know delta VAB is 340, so I can substitute later. So I'll substitute later if I need to. Here will now be half V square. I am looking for VB square, right? So I can substitute already. Q over M is 4.8 times 10 to the power of 7. So generally, when you are doing like a novel substitution like this, or a new equation, my suggestion is move things around until you can see that you can clearly substitute all the values in. That will make it easier for the examiner to check your working and easier for you to double check for mistakes. I am sufficiently satisfied at this point because I can substitute these values in. All right, now I can press my calculator to find my VB directly without writing any more. Because if you write prefix and you keep substituting, so you have to keep rewriting in the next line, that is extra work, my friend. So this will be 1.8 times 10 to the power of 5. Where are the marks? Okay, so the explanation is obviously 1 mark. Either this one or this one is C1. Okay, you substituting the right value here is C1. Final answer is A1. Okay. Of course, some of you may be thinking, can they ask me to find the maximum speed? Sure, but maximum speed is at point M. So we will repeat the calculation. This is just extra for maximum speed. This will be the change in potential in AM, which is 570 minus 140. 570 minus 140. And this will be 430 volt. So what we will do is we will replace this 40 with 430 and we repeat the calculation. There was a past year question that is like this, which is quite nice because it's two calculations, same one. So I'm just going to put 4.8 times 10 to the power of 7. This will be 430 12 Vm square. So we're finding the speed at M. So that would be 2.0 times 10 to the power of 2, 4, 6, 8, 10. 10 to the power of 5. Okay, so the speed at M is the highest and B is not that much slower as well because the change, remember the graph is very steep and then a little bit like this. So here is 2.0 times 10 to the power of 5. Here is 1.8. Makes sense lah. Here is 0 meter per second. Okay, so speed up, fastest at M, slow down. Has it stopped yet? No. So if you want it to stop, you need to actually continue this trajectory and bring it to the same height. Like a normal circular track or a normal inclined plane that you would do in your AS. That's why they define the potential this way. Okay. So this chapter is can be kind of hard if you're not familiar, but if you do some questions, I think it's quite manageable. Because what else can they ask you in the graph? They either ask you to describe the graph, determine whether the charge is positive, negative. Okay, now I'm going to list down all the possible things that they can ask. So, regarding graphs. 1. Determine polarity and magnitude ratio. 2. Describe acceleration, motion speed or force on a particle between charged particle between two charged spheres. They could ask you to calculate the resultant electric field and or sketch E against X graph. Ask you to calculate resultant potential. Potential is very easy one because they are scalar. So you just add and minus like that only. So calculate resultant potential and or sketch VR graph. I ask you to calculate speed of particle at any point in the two or particle. They could also ask you to calculate changes in energy, either EP or EK. Okay lah, we have more or less covered all the possible things that they can ask you with regards to graph. It can also be, this one is generally for two graphs, two particles. For one particle, they can ask you to do all of this as well. Okay lah, but 1 or 2. I think I've covered all of the grounds already. Calculate changes in energy. They could ask you to comment the changes in energy, but that would be a bit on the left field. So if you do practice to make sure that you can answer all of these things, I would say generally people don't do very well with number 2. Acceleration, speed, forces, changes in these things as you travel away and towards in between 2-point charges. The calculation ones are still relatively okay. All right. So this is 1 or 2-point charges for chapter 17. Okay. So I have a department meeting, so I gotta go soon. So I'll stop the recording. But the next afternoon session, what I will do is I will do chapter 18, capacitor. Maybe I will also do op amps, but I may not do communication. So I drag communication to another day lah. So capacitors, right? We are going to talk about parallel plates. But the thing about parallel plates is I'm also going to refer parallel plates to the electric field as well. So capacitor, we'll talk about parallel plates and E field in between parallel plates. It's a bit of a throwback to AS, but with a A2 spin for the parallel plates one. Uniform electric field. Okay, so let's go try questions. Here are the suggested ones to try. Go try. Only 4. Come on. Then how many? 2 here? Yeah, only 6 can do one. So go try the suggested question. If you intend to study this chapter, I think it's okay. It's not that hard. It's just that you will need some time to get used to the way they move the charge around. But for you to be able to unlock any of this thing, you got to know the 4 pillars first. So if you don't know this, or you don't know how to use this properly, then the entire chapter will be hard. And just because you know this doesn't mean you can answer questions. That's the problem with this chapter. And also generally the problem with physics, isn't it? All right, that's it.